In this illustration, we intend to simulate seepage in the soil in the Abaqus software. Actually, we are going to draw the flow net for groundwater flow. In this picture, a long horizontal drainage pipe has been placed in the depth of 4.5 meter under the ground surface. Here you can observe the cross-section of the pipe that is in form of a circle. The diameter of the drainage pipe is 0.6 meter and the thickness of soil is 9 meters. In this picture, you can observe the equipotential lines, and in this one, the flow lines can be observed. And in the next picture, the flow net having been traced for groundwater flow can be observed as well. In fact, we intend to simulate the example 9.11 from Sam Helvani book in the Abaqus software. You can also observe the flow net having been drawn in Sam Helvani book. I will enter the Abaqus software for simulation. Click on Create Part. Select the modeling space as two-dimensional of deformable and shell types and enter the rough size of the tracing page as 40 and continue. Here I'll draw square. The soil is equal to 9 meters high and 9 meters wide. In the next step, I should create the cross-section of the drainage pipe. The cross-section here has a circle-like shape. The pipe lies exactly in the center of the soil. I will put the distance between the center of a circle and this line as 4.5 meters and the distance between this point and this line as 4.5 meters too. As explained in Sam Helvani book, the diameter of the pipe is equal to 0.6 meters. So here I'll enter the radius of the pipe as 0.3 meters and click on Done. In the next step, I'll select Partition, Face, Sketch from Tools menu. Here I will draw a vertical line in the middle of the soil and click on Done. In the next step, I'll enter Property module, click on Create Material. The density of soil is equal to 1,700 kilogram per cubic meter from General Density menu. Then I will select Elasticity and Elastic from the Mechanical menu. The Young module of the soil is equal to 68 megapascal and the Poisson ratio is 0.3. After that, I'll select Pore Fluid, Permeability from the other menu here. The coefficient of permeability that is indicated by K is equal to 5 multiplied by 10 to the power of -7 meter per second. Here I should enter the specific weight of water that is equal to 10,000 and then click on OK. In the next step, I'll click on Create Section. From here, select Solid, Homogeneous, Continue, and OK. Then I'll click on Assign Section, select the whole of soil, Done, and here click on OK. In the next step, I'll enter Assembly Module, click on Create Instance, and enter the soil in the Assembly section. In the next step, I will enter Step Module, click on Create Step. Here I will select Soils, Continue. I will click on Steady State in Pore Fluid Response section. Here the analysis will be done in linear manner. Since we don't intend to calculate the quantity of soil deformation in this question, so the analysis will be done in linear manner. I will take off this option, click on OK. In the next step, I will enter Load Module, click on Create Boundary Condition. From here, select Step 1, then Other, Pore Pressure from the Category section, and Continue. Here I will select the surface of soil and click on Done. Here, a water reservoir with a height of 3 meters will cause a pore water pressure to be applied to the soil surface, and we can calculate the pore water pressure based on this formula. The pore water pressure in this question is equal to rho GH, in which rho is the water density, G is the acceleration of Earth's gravity, and H is the height of water reservoir. Here I will enter the pore water pressure equal to 30,000 Pascal and click on OK. In the next step, I will click on Create Boundary Condition again. From here, select Pore Pressure, Continue. Here, I will select the perimeter of the pipe, click on Done, and consider the pore water pressure equal to 0 for that. In the next step, I will click on Create Boundary Condition. From here, select Initial. From this section, select Mechanical Displacement Rotation. Continue, select the whole of soil and close the boundary condition of U1 and U2 for that. In the next step, I will click on Create Predefined Field. From here, select Other, then Void Ratio, and Continue. Select the whole of soil and click on Done. Put the quantity of Void Ratio equal to 1 and OK. In the next step, I will click on Create Load. From here, I will select Step 1, then Body Force, and Continue. Select the whole of soil and enter the effective specific weight of soil equal to -7,000 and OK. In the next step, I'll enter Mesh Module. Here I will click on Seed Part and enter the granulation size as 0.25. OK. Then click on Assign Mesh Control. Select the whole of soil. From here, I'll select Quad Free and Medial Axis and OK. Finally, I will click on Mesh Part and Yes. After that, I'll click on Assign Element Type, select the whole of soil, and put the element family on the pore fluid, stress, and OK. Here I will save as the model. I'll enter Job Module, click on Create Job. Here we intend to draw the equipotential lines. So I'll click on Submit. The analysis was done successfully. I'll click on Result, then on Plot Contours. After that, click on Comment option, then select Feature Edge. So the meshing would be removed, then click on OK. Then I will select pore pressure from here. Click on Contour option. Here we will put contour type on the isosurface. Click on Apply. I'll put the contour intervals as 8 and click on OK. Here you can observe the equipotential lines. Now if I return to Sam Helwani book, you'll see that the results gained from the Abaqus software are just and quite the same as those gained from this book. Here I'll return to Assembly Module. I'll select Copy Model from the Model menu. Here we intend to draw the flow lines. To do so, I'll enter Load Module. Here I'll click on Boundary Condition Manager. Click on Edit from here. Then on this arrow and select these lines and then click on Done and OK. In the next step, I will click on Edit once again, then on this arrow and select this line, Done and OK. In this manner, AF, CH and EG lines of the pore water pressure equal to 30,000 Pascal will be assigned to them, which you can observe here. Also, a pore water pressure equal to 0 will be assigned to BD line. In the next step, I'll enter Job module, click on Create Job, then on Create, and click on Submit. The analysis was done successfully, so I'll click on Result. Here I will click on Plot Contours, then select Pore Pressure. Here I will put the contour intervals as 6 and OK. You can observe the flow lines here, and if I return to Sam Helwani book, you will observe that the results gained from the Abaqus software are quite the same with those in this book. Now click on Create from the Viewport menu, then select tile vertically. The picture on the left displays the flow lines, and the right picture shows the equipotential lines, and here you can observe both of the results simultaneously.